Okay, we've just dealt with simple transcendental extensions. In this video, we're going to consider a simple algebraic extension. So let's let k alpha over k be a simple algebraic extension. Recall this means that there exists some non-zero polynomial such that when you plug alpha in, you get 0. So let the minimal polynomial of alpha over k be m. Then k alpha over k is isomorphic to the extension, take the polynomial ring, mod out by m over k. And they're isomorphic as extensions, which means where the isomorphism of the base extension is the identity. Okay, so let me say that differently. The isomorphism k adjoin t mod m to k adjoin alpha can be chosen to map t to alpha and the identity on k. And one more thing, this language showed up in the previous video, but can be chosen means there's likely more than one. In general, there's going to be a lot of them, and roughly the choices will lead to different elements of something called the Galois group. But they're saying they are isomorphic, and hey, here's an isomorphism showing it. It's the evaluate t at alpha homomorphism. So this is just evaluate t at alpha. Okay, so let's go ahead and prove that. Well, let's let evaluate at alpha from k adjoin t to k at alpha be evaluated alpha. Let's again let m be the minimal polynomial. Then the kernel of evaluation at alpha is generated by m. This was related to something we said in a previous video. We were talking about the minimal polynomial dividing every polynomial with it at 0. And let's recall a fact. So by the first isomorphism theorem for rings, which you learned in 4600, there exists a homomorphism from the domain ring mod the kernel to k adjoin alpha. And the reason why, well, in fact, there exists a homomorphism which is onto. And the reason why it's onto is because t gets sent to alpha. So all the powers of alpha are going to get hit by all the powers of t. Okay? So we're not only going to get alpha, but if there's an alpha squared, alpha cubed, and if they're all different, we're going to get all of them. It's onto, and the ring on the left is actually a field. Well, the domain ring is a field, let's put it that way. Or let's just even be more precise. And k adjoin t mod m is a field as m is irreducible. Minimal polynomials are irreducible. All right, so we have an onto homomorphism from fields. That's what an isomorphism is. So thus, evaluation at alpha is an isomorphism. Great. Okay, cool. Let me show you a practical use of this. So on homework 1, that's the end of the proof. Well, I guess we should be a little bit proper. And so k adjoin t mod m is isomorphic to k adjoin alpha, and evaluation at alpha fixes k. So it doesn't change the coefficients, obviously, because you're just replacing t. You're not doing anything with coefficients. Okay, end of proof. All right, so example. All right, so on homework 1, let's see, how are we going to color our examples? I think I want to try to stick with blue here. On homework 1, you were asked to show that q adjoin alpha is isomorphic to q adjoin omega alpha, where alpha in R is a real cube root of 2. So alpha is what is typically written as that, and omega is a primitive cube root of unity. Okay. All right, let's see something really cool here, which we'll formalize in a corollary here in a second. Both alpha and omega alpha have minimal polynomial t cubed minus 2. Why? Well, they're both zeros of t cubed minus 2. Okay, check. And t cubed minus 2 is monic and irreducible. All right, that's all we need to do. Great. So, by the theorem, we have two homomorphisms. We have q adjoin t mod t cubed minus 2, and there's a function this way, which is evaluate t at, let's say, omega alpha. And by the theorem, this guy here is an isomorphism. We also have a map, another map out of q adjoin t mod t cubed minus 2, and that's to q adjoin alpha, and this is the evaluate t at alpha map. And by the theorem, this is also an isomorphism. Well, the inverse of an isomorphism is again an isomorphism, as we saw in a previous video. So we can describe an isomorphism by following the purple arrows. Okay? So what is this path? Well, it's undo evaluating t at alpha. So undo it. So replace alpha with a t. And then evaluate t at omega alpha. And that is a function from q adjoin alpha to q adjoin omega alpha, which happens to be an isomorphism because it's a composite of isomorphisms. This strategy for constructing isomorphisms is insanely helpful. So know how to do this. I don't know how many stars I can put, but these ways of constructing isomorphisms between extensions where you share a minimal polynomial, that was the key here. They had to share the minimal polynomial t cubed minus 2. Incredibly helpful. So know how to do this, or know why this works.